Believe it or not, when hurricanes happen, beaches get washed away, like literally gone. They're out in the ocean, in the bottom of the ocean somewhere. And so the tide is removing sand, and this sounds like science fiction, that a pumping station is pumping sand back onto the beach, but it's not. Science fiction, I've seen this done. If you think about touristy areas that rely on beach and tourists and all that stuff for their money, if the beach just goes away, all their money goes away, right? And so they are willing to pony up to pump sand back up to where the beach was and make a new beach. So it's actually pretty realistic. We've seen it done in Florida Panhandle. Beach gone, a couple months later, beach back. Like, okay, didn't know you could do that, but they can do that. So anyways, that's what's happening here. You can see that there is a rate of removal of sand, a rate of addition of sand, and gives you a little more information about units and such, and a time interval. The first little question there says, find the rate at which the total amount of sand on the beach is changing when t equals 4. So this kind of goes back. This is a little bit of a review question from the first part of our unit. The second bullet point is a little more contemporary, and for those that are AB veterans, has a little bit of an extension that perhaps only you would know how to do. The part where it says, what is the minimum value? It involves something we haven't officially talked about in this class yet. And then at what time would Y of t, the total number cubic yards sand on the beach, be maximized? Give graphical reasoning for your answer. Again, the graphical reasoning piece is just to help you navigate some of the details that maybe you might not know about with integrals and definite integrals, that sort of thing, which we'll get to next week. Anyways, so at least give an effort on these. I'll check in with you in a couple of minutes and see how the first one's going, and then kind of progress from there. And we're going to do one more question from the next section, and I suspect that'll be about our time. Yeah, 2:05 is what it says, so we have about a little less than a half hour. We should be able to work through the things we need to work through, but probably not much more. Calculator is active for sure. Jack, Aiden, Forrest perhaps, just because I don't know too much about your past, Forrest. Have you guys ever heard of functions on the calculator? We call them Math 8 and Math 9. You ever heard of those? I'll have to show you those sometime soon. When the calculator's active, those are helpful. Have you ever heard of those? You got the Inspire, so it could be a little different.
Oh, I have a question.
Like numerical derivative, numerical integral. Any question about something?
Oh, yeah. So I press solve. Unless I'm just
No, I don't think it's any quick solving those things.
like just derivative of I kind of forget how to do it.
Yeah, probably. I have to be honest and say I have minimal
Oh, yeah, you told me. I do.
Inspire, solver stuff.
What if I do?
And I think it's that. Oh, no, it's not.
That's your old
I
school.
really just don't appreciate it.
Make a new function where it's x equals.
Yeah, I definitely can get away without using it.
If anyone
It has some awesome features, obviously. But frankly, I just am not willing to spend
I have a
Well, if you're excited for, I can tell you about anything you want to see out for, but I'm not going to be able to help you without doing my own research to figure out. I mean, if I like, honestly, what I would do is I would go here now with Google, how to use the solver on an TI Inspire, and then we do it together. And that would be my method.
Oh, thank God, I can figure it out.
Special insight. All right, let's see how you guys are doing with the first one. Like we said before, this is one of those scenarios where there is competing rates, creating this net rate concept. So how did you guys set up kind of your initial expression, or perhaps you did an equation, I don't know, with the R and the S functions? What? Yeah, good. The tricky thing about this maybe is they presented the functions in the opposite order in which you would probably use them. But Julia, I agree. S of 4 minus R of 4 makes a lot of sense because S is adding sand, R is removing sand, and so I think that order within the subtraction makes perfect sense, and we are concerned about what's happening at t equals 4. This is going to give you a number, presumably some decimal number, right? What'd you get?
-1.908.
You guys agree with that? Negative 1.908?
Oh, wait.
Yeah.
Okay.
909.
909, okay. So like I've said before, we want to be accurate. We want to have correct numbers. But what's the most important thing about that number?
It's negative.
It's negative. So if the net rate of change is negative, what does that mean about the total amount of sand?
It's decreasing.
Oh, someone is trying to steal my screen, but that's...
No.
There we go. Okay. So let's do one more, and that'll be our day and our week. And just a reminder to you, when I see you guys next Wednesday, please make sure that you have brought your unit, or Chapter 4, Unit 2 notes packet, like the next one. So this is that Newton's method thing. This is kind of a cool deal. We just don't have time to do it. We are going to revisit some tangent line stuff and approximations with tangent lines. This is mostly going to be calculator inactive, but we'll do a little bit of calculator active just to make some of the numbers be a little bit easier for you. Okay, so I am hoping that Part A is complete review. Yeah?
Yes.
And relatively straightforward for you. It says, find the equation of the tangent line to the graph of g of x at 5 pi over 8, comma, negative root 2 over 2. We're skipping Newton's method. Newton's method is the bonus topic that I do enjoy doing, but with the minus 9 days, we just don't have time.
On the website, there was a Newton's method on there.
Would you put up?
Was it assigned? It would be, it'd be 3.8. Was it actually assigned?
Well, hold on.
Let's not do it right now because
Okay.
we're on a time crunch. If
I
that
saw something on there about it, and I was like,
if that's coming through on an actual assigned assignment, just let me know and I'll get rid of it. It shouldn't be there, but if it is, I'll fix it. Okay, so perhaps for our new folks who would maybe want a little more direction here, I'll help you out. So it says, find the equation of the tangent line. Asked this question a million times last year. I'll keep asking it. If you're looking for the equation of any line, not to mention just a tangent line, you need two things. What are they?
Slope.
And
The point.
a point. Yeah. Specifically here, it's going to be the point of tangency, which is this point over here, and the slope, which we don't have yet. How do you find the slope of a tangent line?
Use the derivative.
The derivative with respect to x. So this would be g prime of x. A little practice here with some good skills. What would you guys say? And this could just be newbies here if everybody else is kind of doing okay. What would be the derivative of g?
2 cosine of 2x.
And you're using the chain rule, right?
Yep.
Very good. So that is, and this is good because some folks still struggled with this a bit last year. Isn't this the slope of the tangent line for any x value? And we don't really care about any x value. We are most interested in our point of tangency. So I need to plug in that value. So it'd be g prime of 5 pi over 8 equals 2 cosine of 2 times 5 pi over 8. And of course, 2 times 5 pi over 8 is really 5 pi over 4, right? Okay, so then what's the cosine of 5 pi over 4? Unit circle, don't fail us now. Come on. Say again? Yeah. Or if we rationalize it, it's this, right? Second quadrant cosine is negative, and it's a 45-degree angle or a pi over 4 angle, right? So negative root 2 over 2.
Isn't it 10? Yeah, but it's 10 pi over 8.
Which is,
Which is...
5 pi over 4.
which is-
Sorry, third quadrant. Sorry.
I'll go crazy. Wait, what?
So 5 pi over 4. There's pi, and then pi over 4 more.
Yeah.
You multiply that times 2.
yeah, you told me that too.
Oh, times 2. Yep, I forgot that part. So times 2. So how about this for a final? I think sometimes we were talking about two different things. So just negative root 2. There we go. Okay, so then I'm a fan of point slope. I don't know how everybody feels about that, but I would write this as y minus negative root 2 over 2. So it'd be this equals my slope times x minus my x coordinate. And I would call that my equation of the tangent line. You can put that into slope-intercept form if you choose. You You can leave it as point slope. It doesn't really matter unless you're otherwise directed to use a certain form. Okay. Okay, so then this is, again, a little foreshadowing of how we're going to finish this question. So sine of 2x is scrunched up a little bit. I'll just draw it like this. Let's say 5 pi over 8 comma negative root 2 over 2 would be somewhere in here. We'll say maybe like right in here. So the equation of my tangent line would be represented graphically by that red line. Does that more or less make sense? Okay. So then B says approximate g of 2.1, and I feel like a lot of folks get kind of uncomfortable with this word because we're not used to hearing approximate. We want to know what the exact answer is, right? And so we'll use approximation quite a bit. It says to approximate g of 2.1 using the equation of the tangent line. This is where you have to suspend your disbelief a little bit because every year somebody's going to ask the question, well, gee, don't we have g of x right there? Can't we just plug a 2.1 in and get the perfect answer? Yes, I get that. We're definitely leading to something, and we're definitely leading to something even bigger this year. Something called Power Series, which is super cool, which kind of, this is kind of the launch point for it. And so we're not going to always be able to have g of x. And so I will politely say, don't worry about the fact that we already have g of x. I get it. We're going to use the line to approximate this, and this will lead us to much bigger and much better things. Okay? So what you do with this, of course, y plus root 2 over 2 equals negative root 2 times 2.1 minus 5 pi over 8. And this would be where you'd use your calculator and evaluate everything, and you'd get some nice decimal answer. Yes, sir?
Is it okay if we leave it like that?
You totally could. That's maybe even better because we don't even have to round anything off that way, huh?
Yeah.
So that's fine. So Sam just basically added the root, or he subtracted the root 2 over to the right side, and that's perfectly acceptable. In fact, if we wanted to, why not write that? I'll go y equals negative root 2 times 2.1 minus 5 pi over 8 minus root 2 over 2. This is approximately equal to g of 2.1. And if you want to get a decimal, you certainly could, but this would be a perfectly good answer. Okay, so in our last few minutes here, we're going to talk about the final question being, is the approximation from part B too high or too low? And I think you can probably look at the graph and get an idea. So within the neighborhood close to the point of tangency, would you guys guess that the red line is higher than the purple graph or the other way around? Yeah, red line appears on the graph at least to be lower. So, graphically speaking, we'd probably guess, I'm thinking it's probably going to be too low, right? The purple graph is always going to be above my approximation for that little area around my point of tangency. And here's how we actually can numerically do it. We're going to have to use the second derivative. So I'm going to write that out. My second derivative, g double prime of x equals negative 4 sine of 2x. That make sense? Okay, so I want to find out, essentially, is the purple graph concave up or concave down for the interval that I care about, and that'll give me to my answer. So the way I find this is I'm going to set this equal to 0, because that's how you find out where concavity might be changing. And I divide through by negative 4, I get sine of 2x equals 0. Then I get 2x equals the inverse sine of, where is sine 0? 0 and pi, 2 pi, so on and so forth. So then x would equal 0, pi over 2, pi, et cetera, et cetera. Well, where does 5 pi over 8 fit into that? Like between which numbers?
Between pi and 3 pi over 2.
Oh, isn't it between
I know.
pi over 2 and pi? 5/8 pi, just like a little bit bigger than half pi.
Yeah.
Where does the 2.1 fit? Does it fit in the same interval?
Yeah.
It does, right? Because pi over 2 would be roughly 1.5, and pi we know is roughly 3.14 approximately. And so both of those numbers fit within that interval. So we do just a brief little sign chart here. We figure out what's going on. What's happening between pi over 2 and pi? what would you guys say? What would be a good number to plug in between there? Say again?
We don't know, never mind, that's on the other side.
Well, pi over 4 is on the left. 3 pi over 4. Okay, so let's do this mentally. If I plug a 3 pi over 4 in there for x, wouldn't it become 3 pi over 2? And what's sine of 3 pi over 2? -1 times -4. Yeah, so we could say g double prime of x is going to be positive on the interval from pi over 2 to pi, which contains our two key points, right? The point of tangency as well as our approximating point. So if g double prime is positive, that means the graph of g is what? Concave up, right? Because g double prime is positive, right? I do that sometimes too. Don't worry about it. So if g is concave up, which we've just kind of confirmed that the purple graph is actually accurate for the most part, that means my approximation is indeed too low. So if you can prove that the second derivative is positive on the interval that we care about, we can say therefore the APX approximation is too low. If we found out that g double prime was negative on that same interval, then we'd actually say that tangent line is too high, right? The tangent line would be above it the entire interval. So proving that an approximation is too high or too low using a tangent line, we use the second derivative. And we'll do with some other approximations later on. But that's kind of the gist of it. There's one other example. I'll leave the old video up because the old video has it has the other example on there too. I'll just add this to the library so you get a full picture of things. So Santi, your question.
How'd you choose your A?
So I set g double prime equal to 0.